Imagine looking up at the night sky before the year 1608.
Okay.
So no city light pollution, just you standing in the dark, staring up.
Right. Beautiful.
Yeah, and for thousands of years of human history, every single person who looked at that sky saw the exact same thing. Just this black ceiling, dusted with tiny, glowing, completely static dots.
Just pinpricks of light.
Exactly. And we charted them, we used them to navigate, we even built massive mythologies around them. But fundamentally, to the naked eye, a star was just a dot.
It was completely unreachable.
Unreachable and mostly unknowable. And then a few glassmakers in the Netherlands put two curved lenses inside a tube, right? Galileo refines it, and someone finally points a telescope upward.
And the universe didn't actually change in that moment, but our entire conceptual framework of reality it completely shattered.
Right. The dots became spheres.
They became actual places.
Yes. Suddenly we could see craters on the moon or, the rings of Saturn, the moons of Jupiter. We realized those tiny little dots were these massive, chaotic engines of nuclear fire.
Burning across distances we couldn't even fathom at the time.
Right. The telescope didn't invent the cosmos. It just gave us the visual vocabulary to finally comprehend what had been there all along. And we are kicking off today's deep dive into the source material with that specific historical feeling because we are, right now, staring down the barrel of a very similar telescope moment.
A biological telescope moment.
Exactly.
Hmm.
But instead of looking up at the void of space, we're looking inward, down into the microscopic galaxies of living cells inside your own body.
It is a really stunning parallel to draw, because for the last century, our view of cellular biology has been incredibly sophisticated, but still, fundamentally, it's been limited by our tools.
We've been looking at dots.
We've been looking at the biological equivalent of static dots, yeah.
Hmm.
And the source material we are exploring today, it outlines a technological infrastructure that aims to give us the full dynamic movie of life.
Yeah, we are pulling from a deeply comprehensive and honestly a totally perspective-shifting document today. It's titled PreciGenetics, the technology that lets us watch life think.
By Paramendra Kumar Bhagat and Parmita Mishra.
That's right. And the mission of this deep dive is to really explore this radical technological moonshot they're building. We're going to examine how they are combining photonics, so the deep physics of light, with microfluidics and artificial intelligence.
To do something that, honestly, it sounds like complete science fiction.
It really does. Watching living, breathing cells make active decisions in real time.
And the stakes for this, they could not be more personal for you or me or literally anyone listening.
Right.
Because modern medicine, for all its absolute miracles, it still relies heavily on statistical guessing, especially when it comes to complex diseases like cancer.
Yeah, trial and error.
Exactly.
Yeah.
We treat patients based on what works for the quote-unquote average person, largely because biology right now operates in a state of half-blindness.
Which is terrifying when it's your life on the line.
It is. But if the underlying technology, PreciGenetics, is developing this platform they call Compass, if it actually scales, it promises to drag medicine out of that era of trial and error.
And into what?
Into an era where disease becomes a predictable, computable engineering problem.
Okay, let's unpack this.
Yeah.
Because to understand the sheer scale of the solution they're proposing,
Yeah.
we have to completely rethink the enemy. We have to strip away the simplistic ways we're often taught about illness.
The whole invader narrative.
Right, and look at the grim mechanical reality of why cancer has managed to outsmart trillions of dollars of research.
Yeah, the first conceptual hurdle here is redefining the human body itself. Because we tend to experience our bodies as single, unified machines. You look in the mirror, you see one person.
Naturally.
But biologically, you are a civilization. You are a walking, breathing planet populated by roughly 30 to 40 trillion individual living cells.
30 to 40 trillion. That is a society that massive only functions if there are incredibly strict rules.
Strict and sometimes incredibly ruthless rules. Cells in your body are constantly dividing, performing their specific functions. So whether that's a heart muscle cell contracting or, a retinal cell catching light.
They all have jobs.
Right. And crucially, when they are damaged or when they get too old, they are programmed to sacrifice themselves for the good of the whole.
Right, the document talks about this, apoptosis.
Yes, apoptosis, programmed cell death. The health of the entire civilization depends on millions of cells quietly dying every single second.
Which is wild to think about. And cancer is basically what happens when a cell just refuses to die.
It rejects the programming.
Right. The source makes a point that I think gets lost in public awareness campaigns, which is that cancer is not an invader. When you get a cold, that's an external virus breaching the walls. A bacterial infection is an invading army.
Right, they come from the outside.
But cancer is a rebellion from within. It is your own biology, your own citizens rewriting the rules to serve only themselves.
And that internal origin is exactly what makes it so devastatingly difficult to fight, because you are trying to kill a rogue faction without destroying the entire city.
Right, without killing the patient.
Exactly. And the rogue faction's primary weapon isn't just its ability to divide rapidly. Its greatest weapon is adaptation. Cancer is not a static lump of tissue. It's an active, accelerated evolutionary process playing out inside the host.
Which brings us to a phenomenon the authors call the illusion of victory. And I really want to linger on this because it is the tragic reality for millions of families.
It's heartbreaking.
It is. A patient gets diagnosed, they go through brutal chemotherapy or radiation. After months of this, the scans come back clear. The tumor has shrunk down to the point of being totally undetectable.
The doctor declares remission.
Right. The war feels won. But then, a year or two later, the cancer returns. And when it comes back, the drugs that worked the first time, they do absolutely nothing.
Nothing at all. It's a devastating cycle, and it happens because of the raw mechanics of natural selection.
How so?
Well, when an oncologist administers a traditional broad-spectrum chemotherapy, they are introducing an extreme toxic stressor into the tumor's environment. The drug acts as a massive evolutionary filter.
Like a sheer cliff face.
Yes. It acts like a sheer cliff face.
And it kills, what, 99.9% of the cells because they just don't have the gear to climb the cliff.
Exactly. The vast majority of the cancer cells are vulnerable to the poison, so they die, and that's why the tumor shrinks on the scan. But a tumor of any significant size contains billions of cells.
Right.
So statistically, sheer random variation means that a tiny fraction of those cells might possess a slight biological quirk.
Like what kind of quirk?
Maybe a slightly thicker membrane or a microscopic pump that actually pushes the chemotherapy toxin back out of the cell before it can do any damage.
Oh, wow. So the chemotherapy effectively clears the battlefield of all the weak competition.
Exactly.
And it leaves all the nutrients in space for the few microscopic survivors who already knew how to beat the drug.
That is the grim reality of it.
Yeah.
Those survivors hunker down, they survive the treatment, and eventually they begin to divide again.
Wow.
Only now, the entire new tumor is built exclusively from the genetic lineage of the cells that resisted the drug.
So you aren't fighting the original disease anymore.
No. You are fighting Cancer 2.0. It's an upgraded, battle-hardened variation that is fundamentally immune to your primary weapon.
See, I understand the natural selection part.
Yeah.
Where the survivors reproduce. But the source completely shattered my understanding of how these cells change their behavior in the first place.
Mechanism of it.
Right. Because growing up, the basic biology lesson is always, DNA is destiny. DNA is the master blueprint.
Right.
If a cell mutates and becomes cancer, it's because the blueprint itself got a typo in it, right?
That is the foundational view of genetics, yes. A mutation in the DNA sequence, an actual literal change in the genetic code, can trigger cancer, but the authors highlight that genetic mutation is only half the story.
And the slower half, apparently.
Much slower. The much faster, more insidious way cancer adapts relies on a totally different system called epigenetics.
The document uses a really elegant analogy here. They say if your DNA is a grand piano, it contains all the keys necessary to play every conceivable song.
Every single note.
Right. But a piano sitting in an empty room doesn't make music.
Yeah.
It doesn't decide the tempo or the volume or whether it's playing a waltz or a funeral march.
For that, you need a pianist. You need something actively interacting with the keys. In cellular biology, epigenetics is the pianist.
Okay.
The prefix epi means above or on top of, so epigenetics is the chemical control system sitting directly on top of the DNA. It decides which genes are turned on, which are turned off, and exactly how loudly they're expressed.
I want to make sure I really grasp the physical reality of this, because if all the cells in my body have the exact same DNA, like my skin cells have the same blueprint as my brain cells.
Yes, identical blueprints.
How does epigenetics physically stop a skin cell from trying to grow a neuron? Is it blocking the blueprint somehow?
It literally blocks it. Let's look at one specific mechanism they mentioned called DNA methylation. Imagine your DNA is a massive, coiled-up library of instruction manuals. If the cell wants to ensure a specific manual is never read, it attaches tiny chemical tags, these are called methyl groups, directly onto the DNA strand at that specific location.
Like physical tags.
Right. And these tags act like superglue. They force the DNA to clump together so tightly that the cellular machinery responsible for reading the genes physically cannot pry the pages open.
Oh, wow.
The gene is still there, the sequence hasn't mutated at all, but it has been permanently silenced.
So a skin cell has the grow-in neuron instruction manual literally superglued shut.
Exactly that. And another mechanism involves things called histones.
Histones.
Yeah, they're the protein spools that DNA wraps around to keep itself organized, because DNA is incredibly long.
Right.
If the epigenetic system alters those spools, it can unravel a section of DNA, leaving it wide open and easily accessible, effectively turning the volume of that gene all the way up.
This completely explains the identical twin phenomenon they mentioned.
Yes, a perfect example.
Because two humans can be born with the exact same genetic sequence, the exact same piano. But over decades of life, let's say one twin lives in a polluted city and smokes, while the other lives in the mountains and eats well.
Different environments.
Right. And at age 60, one gets a disease, the other doesn't. Their DNA is still identical, but their epigenetic sheet music has been completely rewritten by environmental stress.
That is the raw power of the epigenetic switchboard. It is highly responsive to the environment. And cancer is an absolute master manipulator of this switchboard.
So it's actively playing the keys.
Yes. A cancer cell facing a toxic wave of chemotherapy doesn't necessarily need to wait for a random genetic mutation to save it. It can sense the stress and epigenetically alter its identity right then and there.
Ow!
It can slap methyl tags onto its self-destruct genes, supergluing them shut, while simultaneously unraveling the genes that build microscopic pumps to flush out the chemo.
It's changing its disguise in the middle of a bank robbery without actually changing its fingerprints.
That's a great way to put it.
But wait, I have to challenge something here. Let's wind the clock back a bit to the early 2000s. The Human Genome Project was completed. It was this massive, multi-billion-dollar international effort.
A huge milestone.
Right, and the headline everywhere was basically, "We have decoded the instruction book of human life."
I remember.
So if we have the complete map of human DNA, why didn't that solve cancer right then and there? If we know all the genes, shouldn't we be able to build a drug for every problem?
It's a completely rational expectation, and honestly, it was a pervasive belief at the time, even among scientists. But it confuses the map with the territory.
Okay.
The Human Genome Project gave us an incredibly precise topographical map of the human blueprint. It shows us exactly where every genetic mountain, river, and valley is located. But a topographical map does not tell you the current weather.
It doesn't tell you if it's raining right now?
Exactly. It doesn't tell you if the river is currently flooding or if a blizzard has made the mountain pass impassable. Epigenetics is the weather. It is dynamic, constantly shifting, and highly localized. Having the genetic map is a monumental achievement, of course, but if you don't know the epigenetic weather patterns happening inside a tumor at this exact second, you are still navigating in the dark.
Which brings us crashing into the core bottleneck of modern biology. The authors call it the snapshot problem.
Yes.
Because if cancer is constantly shifting its epigenetic weather, turning genes on and off to survive drugs, why haven't scientists just set up a microscope and watched it happen? Why is it such a mystery?
It seems like an obvious solution.
Right. But it turns out the tools we use to study life are fundamentally terrible at observing time.
The document uses an analogy of a bird in flight to illustrate this limitation, and it perfectly captures the frustration of the entire field.
I love this analogy.
It's so good. Imagine you are an alien scientist and you're trying to understand the complex aerodynamics of how a bird flies. But you are forbidden from watching a video. You are only allowed to look at 2 static photographs.
Photograph 1. The bird is hovering in the air. Photograph 2, taken an hour later, the bird is sitting on a branch.
From those 2 static snapshots, you can deduce a lot. You can measure the wingspan, you can catalog the feathers, you can calculate the distance traveled between the 2 points.
But you missed the flight.
You miss the entire physics of flight. You miss the flapping, the way the bird adjusts to a sudden gust of wind, the mid-air decisions it makes to avoid a predator. You miss the continuous dynamic process that connects state A to state B.
You missed the movie. And when I dug into the source's explanation of modern lab techniques, my jaw actually dropped. Because we hear these terms on the news, words like sequencing or biomarker analysis.
Right.
And we just assume scientists have this magical clear window into the cell. But to get these incredibly high-resolution snapshots, biologists almost always have to destroy the thing they're studying.
It is the great paradox of biological research. To understand how a cell lives, you generally have to kill it.
Let's look at some of these gold standard tools mentioned in the text, because I think understanding how they actually work reveals exactly why we're stuck. Take sequencing, for example, which is how we read DNA and RNA.
Ugh.
How do you actually get a sequence out of a tumor biopsy?
It is a highly destructive process. You take the living tissue and you use chemical detergents to literally liminalize the cells, meaning you burst their outer membranes open.
So you dissolve the protective walls.
Completely. Then you use enzymes to chop the DNA or RNA into millions of tiny fragments so a machine can read the chemical letters. You get an incredibly detailed list of the genetic code. But the cell is entirely pulverized. It's a smoothie.
A biological smoothie. What about flow cytometry? That's another huge one. The name itself sounds so gentle, like you're just watching things flow by.
It is slightly more intact than sequencing, but still highly traumatizing for the cell. In flow cytometry, you suspend cells in a fluid and force them through a nozzle so microscopic that they have to pass through single file. And as they pass, you hit them with a laser to measure their size or look for specific proteins. But to get them to separate out of a solid tumor in the first place and survive the sheer physical pressure of that tiny nozzle, the preparation steps are brutal.
How brutal.
Well, the cells are ripped from their environment, often chemically fixed, which means freezing all their internal structures in place with chemicals.
So they aren't even really alive anymore.
Right. By the time the laser actually hits them, they are dead or functionally paralyzed.
So all of these techniques, Western blotting, ChIP-seq, ATAC-seq, they're just incredibly advanced forms of biological archaeology.
Exactly.
You are digging up the ruins of a cell to guess what it was doing before you destroyed it. But wait, surely scientists have ways of looking at living cells under a microscope. I mean, we've all seen videos of amoebas moving around in high school biology.
They do, but that introduces the second major hurdle they discuss, the label problem. Under a standard light microscope, the internal machinery of a human cell is mostly transparent.
It's all just water and clear proteins.
Right. It's like trying to find a clear glass marble inside a pool of water. To actually see a specific protein or to watch a specific gene turn on, scientists have to use labels.
Like dyes.
Yeah. They engineer the cell to produce a fluorescent protein, or they attach chemical dyes that glow under certain wavelengths of light.
And the source points out why this is fundamentally flawed. If we go back to our bird analogy, labeling a cell is like forcing the bird to wear a massive, glowing, heavy GPS tracker bolted to its wing.
It physically alters the very behavior you were trying to observe.
Yeah.
If you attach a bulky chemical fluorescent tag to a delicate protein inside a cell, that protein might not fold correctly anymore.
It changes the physics of the cell.
Yes, it might not interact with its neighbors the way it naturally would. Furthermore, to make those dyes glow in the first place, you have to blast the cell with intense concentrated light.
Which causes something called phototoxicity, right?
Yes. High-energy photons hitting those chemical dyes can create highly reactive oxygen molecules inside the cell.
Which is bad.
Very bad. These molecules act like microscopic shrapnel, literally shredding the cell's internal structures.
Good Lord.
So not only is the cell wearing a heavy backpack, but the flashlight you are using to track it is actively giving it radiation poisoning. The cell becomes stressed, it changes its behavior to deal with the stress, and the data you collect is compromised.
Plus, there's the issue of bias, right?
Yeah.
Because if you only have 3 colors of fluorescent dye, you can only label 3 specific proteins.
Right, you have to choose.
You have to decide in advance what you are looking for. So if the cancer cell figures out a way to survive, using a completely different protein pathway, one you didn't think to label it, escapes entirely unnoticed, it pulls off a heist off camera.
What's fascinating here is that the true cost of the snapshot era isn't just, academic frustration. It has a catastrophic real-world cost.
For patients.
Yes, because we can only measure the before and after states, the tumor before the drug, and the resistant tumor that grows back 6 months later. We are completely blind to the critical window between those moments.
The actual evolution.
We miss the exact sequence of events where the cancer cell figures out the puzzle and rewrites its epigenetic survival manual.
And because of that blindness, the traditional model of drug discovery is basically broken. The text notes that developing a single new drug takes 10 to 15 years, costs billions of dollars, and in oncology specifically, it faces a staggering 97% failure rate.
97%. Imagine any other industry where 97% of the products completely fail after billions in investment.
it wouldn't exist.
Right. And that happens because a drug might look incredibly effective when tested on a frozen static cell in a lab. It kills the cells in the snapshot.
But in the body.
When you put that same drug into the dynamic, living, adapting environment of a human body,
Yeah.
cancer just shifts its epigenetic weather and ignores the drug.
Okay, so we are at a total impasse here. If we grind cells up, we destroy the movie. If we use chemical markers to label living cells, we poison them and change their behavior. How on earth do you observe the complex internal decision-making of a living cell without touching it, labeling it, or killing it?
It seems impossible.
It does, but this is where the physics gets incredibly cool. The authors propose using the oldest, most ubiquitous messenger in the universe, light.
We really have to move away from thinking of light merely as a tool for illumination. Light is a carrier of high-density information. Every single time a photon, a fundamental particle of light, interacts with matter, it takes a piece of information about that matter with it.
Astronomers have been exploiting this for centuries. If we want to know what a star a billion light years away is made of, we don't build a probe and fly it there. We just catch the light the star emits.
That field is called spectroscopy, and it is the exact same foundational physics being applied here, just at a microscopic scale.
Inside a human cell.
Exactly. Every molecule in the universe has a specific structure. The atoms in a protein or a lipid are held together by chemical bonds. You can think of these bonds like tiny invisible springs connecting the atoms.
And different springs have different stiffness. Like a carbon-oxygen spring bounces differently than a carbon-hydrogen spring.
Precisely. When you shine a broad spectrum of light onto a cell, the photons hit those molecular springs. Some of the light is absorbed, transferring its energy to make the springs vibrate. Some of the light bounces off or scatters.
Okay.
Because every type of molecule has a completely unique set of springs, it will absorb and scatter specific, exact wavelengths of light.
So the light that bounces back out of the cell is missing certain colors or has shifted frequencies. It carries a signature.
It carries a highly complex optical fingerprint of everything inside that cell. And this isn't just about identifying chemicals, it's about physical architecture.
Right.
Let's go back to the epigenetics switchboard for a second.
The superglue.
Right. We talked about how a cell might superglue a gene shut to survive a drug, causing the DNA to clump up tightly.
Like the chromatin packing.
Yes. When DNA packs together tightly, it physically changes the density of that specific region inside the cell nucleus.
Think about looking at a spoon sitting in a glass of water.
Oh, how it looks bent. Right. The spoon looks bent or broken at the waterline because water is denser than air, which changes the speed and angle of the light passing through it. That bending is called the refractive index.
Oh, I see where this is going. So if a cancer cell is actively changing its epigenetics, if it is scrambling to pack away its self-destruct genes and unpack its survival genes, the physical density of its nucleus is shifting in real time.
And that shifting density changes the refractive index of the cell. The way the light bends and scatters as it passes through the nucleus actively changes.
So you can literally see it reacting.
By continuously reading those shifting spectral signatures, scientists can literally watch the physical footprint of the cell's epigenetic state changing. They can see the cell becoming stressed or see it shifting into a resistant state, entirely label-free.
You don't need a heavy glowing GPS tracker.
You just read the photons.
Okay, I have to play the skeptic here because this sounds almost too clean. A human cell is a chaotic soup of water, thousands of different proteins, fats, sugars, and massive strands of DNA.
Very messy.
You shine a light on that soup, and it bounces back millions of interacting waves. It's not like the light comes back with a neat little text message saying, "Hello, I am currently unpacking chromosome 4 to resist chemotherapy."
No, it definitely doesn't.
That raw data must be an incredibly messy, overlapping catastrophe.
Oh.
How do you separate the signal from the noise?
Your skepticism is entirely warranted, and it is exactly why this approach, despite the physics being understood for a long time, has been practically impossible until very recently.
Okay.
The raw spectral curve bouncing off a living, changing cell looks like pure, chaotic noise to a human observer. To decode it, you need two things that didn't exist a decade ago: a revolutionary hardware environment to isolate the signal, and a radically new type of software to interpret the noise.
Enter the hardware. Compass. This is the platform PreciGenetics is building. It stands for Continuous Optical Measurement and Predictive Analysis of Single Cells, or something close to that in spirit.
Close enough.
It's the machine built to watch life think. And to solve the noise problem, it relies on a field of engineering called microfluidics. Now, the authors describe this as plumbing for tiny worlds, which is a really fun visual. But what does it actually mean to build pipes for a cell?
It requires engineering on a scale that is genuinely difficult to conceptualize. A typical human cell is roughly 10 to 20 micrometers across.
Which is?
That is a fraction of the width of a human hair. Microfluidics involves carving channels and chambers into glass or polymer chips that are precisely that small.
Why go through the nightmare of building microscopic plumbing? Why not just put a bunch of cells in a petri dish and shine a light on the dish?
Because of fluid dynamics. If you put cells in a petri dish or a test tube, the liquid is chaotic. There are convection currents, temperature gradients, and the cells are tumbling all over each other.
Just floating around.
Right. It's impossible to track one specific cell over time. And it's impossible to guarantee that the drug you drop into the dish reaches every single cell at the exact same concentration.
It's like trying to interview one specific person in the middle of a mosh pit at a rock concert.
Exactly. Microfluidics removes the mosh pit. At the microscopic scale, fluids behave very differently. They enter a state called laminar flow.
Laminar flow.
Yes, where the fluid moves in perfectly parallel, predictable sheets without mixing. A microfluidic chip allows scientists to take a chaotic soup of cells and flow them into these channels so they are perfectly isolated.
So you trap a single cancer cell in a tiny, perfectly controlled chamber.
You hold it in place. And because the plumbing is so unbelievably precise, you can control its environment with absolute perfection.
Yeah.
You can wash a precise concentration of oxygen over it. You can introduce a nutrient, or, crucially, you can introduce a specific dose of a new cancer drug.
Wow.
And while the cell is locked in this controlled microenvironment, you hit it with the continuous beams of light to capture its spectral fingerprint.
You aren't slicing it open, you aren't staining it, you are just holding it in a gentle, microscopic river and watching it react.
Yeah.
You can watch it for hours or even days. You've successfully moved from biological archaeology to biological cinematography. You are filming the movie.
And that transition to cinematography, capturing the unbroken timeline of a living cell's reaction, is the ultimate goal. But there is a philosophical pillar to the compass system that is just as important as the physics of the light.
What's that?
It's the emphasis on the single cell.
Right. Why go through the agonizing engineering challenge of trapping cells one by one? If a tumor has 1 billion cells, wouldn't it be faster to just measure chunks of it at a time? This brings us to a concept the source material tackles called the tyranny of averages. I thought their explanation of this was brilliant.
It is a critical flaw in how we currently understand disease. Think of it this way. If you want to understand the political dynamics of a highly polarized country before an election, you don't walk into a stadium of 100,000 people and ask them to shout their opinions simultaneously,
Right.
and then try to measure the average volume of the noise.
If you did that, you'd get some incredibly bland average statement that represents absolutely no one in the room. You would completely miss the extreme radical factions on the fringes.
Exactly.
And those fringe factions might be the ones highly motivated enough to actually swing the election.
That is exactly what traditional bulk biology does to a tumor. In a standard clinical setting, a biopsy is taken. That piece of tissue contains millions of cells. The lab grinds the entire tissue up into a molecular soup and measures the average genetic expression or protein levels of the entire mass.
But tumors are not uniform. They are incredibly diverse ecosystems.
They are wildly heterogeneous. So imagine a scenario where a patient takes an experimental drug. The drug is incredibly effective against the dominant type of cell in the tumor. In the bulk soup, let's say 9,999 out of 10,000 cells are screaming, "We are dying, the drug is working."
So the bulk average looks phenomenal. The doctor reads the report and says the drug is a total success.
But hidden in the noise of that average is one single cell out of the 10,000. And that one cell happens to have a slightly different epigenetic profile.
The fringe faction.
Yes, it isn't dying. It is hunkering down, altering its refractive index, unpacking its survival genes, and completely ignoring the drug. Because you ground everything into a smoothie, the signal of that one surviving cell is completely drowned out by the noise of the thousands of dying ones.
And what happens to that one cell? It's the seed. It survives the treatment, waits a few months, and repopulates the entire tumor. It's what we talked about at the beginning, the illusion of victory.
Clinically, this phenomenon is often referred to as minimal residual disease, or MRD. It is the invisible, underlying cause of relapse. The source text also highlights the role of cancer stem cells.
What are those?
These are incredibly dangerous minority cells within a tumor that act like regenerators. When they sense the toxic stress of chemotherapy, they don't fight it. They enter a state of deep dormancy.
It's like hibernation.
They literally hibernate. They stop dividing, they shut down their metabolism, and they can hide in bone marrow or tissue for years, completely undetectable by standard scans, only to awaken a decade later and seed a completely new tumor.
So if you want to actually cure the disease, you can't just kill the bulk of the tumor. You have to hunt down the outliers. Precision medicine is useless if it's based on an average. It has to start at the single-cell level.
Which is why COMPASS slows the cells individually. By capturing the spectral fingerprint of every single cell one by one, you don't lose the outliers in the average. You can actually see the one cell out of 10,000 that is shifting into dormancy.
Okay, I am entirely sold on the necessity of looking at single cells. But the logistics of this brings us to an unavoidable cliff.
The data problem.
Yeah, if you are flowing millions of single cells through these microfluidic channels, and you are hitting each one with light, capturing thousands of different wavelengths every single second over a period of days, the amount of data being generated is beyond astronomical. It's not just a haystack, it's a mountain range of haystacks.
Yeah.
How is any human scientist, or even a team of scientists, supposed to look at billions of squiggly spectral lines and decipher what they mean?
They can't. It is a biological impossibility for a human brain. Human pattern recognition is an incredible evolutionary tool. We are great at spotting a predator in the bushes or recognizing a face, but our brains max out at 3, maybe 4 dimensions of data.
Right.
The spectral fingerprint of a single cell fluctuating across thousands of wavelengths over time represents a mathematical space of thousands of dimensions.
It's like listening to a chaotic symphony orchestra of 10,000 instruments and trying to isolate the sound of one slightly out-of-tune violin.
Yeah.
It just sounds like noise.
But what is noise to a human brain is a rich, navigable landscape for an artificial intelligence. AI acts as the ultimate biological translator for the COMPASS system. It doesn't replace the scientist. It serves as a completely new sensory organ capable of perceiving high-dimensional mathematical spaces.
So you feed the raw, messy light data into the AI. But how does the AI actually know what it's looking at? I mean, I've used AI chatbots, and they hallucinate facts all the time. How do we trust an AI to tell us a cancer cell is going dormant?
That is the crux of the problem, and it requires a fundamental shift in how we train biological AI. Historically, AI models in biology have been starved of the right kind of data. We've been feeding them the snapshots.
Because that's all we had.
Exactly. The era of omics, genomics, proteomics, transcriptomics has generated massive databases of static information.
We gave the AI millions of photos of the bird on the branch and the bird in the air.
And we asked the AI to predict how the bird flies. But if you want to train an AI to understand dynamic behavior, static data is useless. Imagine trying to train a self-driving car AI by only showing it photographs of empty roads and photographs of crashed cars.
It would never learn how to actually drive.
It will never learn how to steer, how to brake, or how to navigate traffic. To learn behavior, the AI needs continuous video. It needs sequences of cause and effect.
The source calls this necessary shift moving from omics to dynamics, or chronomics, the study of biology across time.
Because the COMPASS hardware is finally capable of generating that continuous, non-destructive video of living cells, they can finally feed the AI the time series data it actually needs.
So it's a loop.
The system operates in a closed loop. First, the microfluidics trap the cell and expose it to a drug. Second, the photonics capture the shifting light signatures minute by minute. Third, the AI processes that massive data stream to classify the state of the cell.
Wow.
It learns the mathematical pattern that correlates with healthy, stressed, or dormant.
But because it's watching over time, it doesn't just describe what the cell is currently doing. It learns the trajectory.
Yes. The predictive power is the holy grail. The AI watches enough cells react to enough drugs that it begins to recognize the early warning signs. It can look at a cell's spectral fingerprint and say, this cell currently looks healthy, but its trajectory indicates it is actively moving toward a drug-resistant state.
Like forecasting a hurricane.
Precisely. It can say, in 48 hours, this cell will be immune to your chemotherapy.
It turns biology from a descriptive science into a predictive data science. It shifts the fundamental question from, what is this tumor made of, to what is this tumor going to do next?
And achieving that level of predictive power requires an infrastructure undertaking that borders on the absurd, which really transitions us from the theoretical science into the human element of this story.
Yeah, who actually has the audacity to try and build a machine that translates the language of life?
Right, we have to talk about the founder of PreciGenetics, Parmita Mishra.
The background provided in the text paints a picture of someone operating with an incredible amount of grit and a healthy dose of defiance. She officially started the company in 2024, and she didn't start it in some billion-dollar pharma lab. She started it with $1,000 and a personal loan from a loved one.
It is the classic, almost mythical garage startup origin story, but applied to highly advanced quantum biology. And she faced intense skepticism. The document notes that early on, people told her she belonged in an asylum for thinking she could pull this off without massive institutional backing.
But she has this fierce philosophical drive. There's a quote of hers in the text that I love. She says that building the future requires a certain level of delusion turned into reality through relentless, persistent engineering. Brilliance cares for science, not sanity.
It's a great quote.
And what I find most fascinating about her approach is what she actively refused to do when starting the company.
The standard playbook for a biotech startup is designed to minimize risk and appease venture capitalists quickly. You find a narrow problem. You develop a single diagnostic test for one specific disease, or you try to discover one specific drug molecule.
Right.
You get it working, you patent it, you sell it to a major pharma company, and you exit.
It's building a slightly better flashlight. But she completely rejected the easy product. She didn't want to build a better flashlight. She wanted to wire the entire house for electricity. She opted to build the underlying infrastructure layer.
The analogy the authors use here is incredibly potent, building the AWS of biology.
AWS being Amazon Web Services.
Yeah.
I think most people interact with the internet every day without realizing that massive chunks of it, from Netflix to banking apps, all run on Amazon's physical servers.
Right. Before AWS existed, if you wanted to start a software company, you had a massive physical hurdle. You had to buy physical server racks, lease a climate-controlled room to put them in, hire engineers to wire them, and maintain the hardware. It was expensive and slow.
Very slow.
AWS built massive server farms and turned computing power into a scalable utility. You just log on, rent the server space you need for a few bucks an hour, and focus on building your software.
PreciGenetics wants to do the exact same thing, but for dynamic biological observation. They don't want to be a company that just discovers one cancer drug. They want to build the massive physical compass facilities so that every pharmaceutical company, every university researcher, and every clinical oncologist can log in and rent time on their machines.
The goal is to make high-dimensional single-cell analysis a standardized utility. If a lab in Boston invents a new drug compound, they don't need to spend 10 years testing it on dead cells.
So they just send it over.
They can send their compounds to the PreciGenetics facility, run it through the microfluidic chips against thousands of living cells, and get the predictive AI trajectories back in days.
It is a 20-year moonshot. The appendices of the document lay out this incredibly aggressive roadmap. They've already secured backing from the 1517 Fund, which is notable because that fund specifically targets non-traditional founders and dropouts who are building deep tech.
They look for outliers.
Exactly. They're currently operating out of the MBC Biolabs in California, iterating through their early hardware, Proto-1 and Proto-2.
But the scale of their ambition is in the next phase. By 2027, they aim to build the Arizona Luma facility, which is designed to be a massive, high-throughput industrial complex. And their ultimate target is to establish a $1 trillion planetary infrastructure layer by 2045.
I have to pause here and channel the skepticism she faced early on. It is one thing to build a cool microfluidic chip in a lab. It is an entirely different universe of difficulty to build an automated planetary-scale infrastructure that handles millions of living biological samples, processes petabytes of optical data, and spits out flawless AI predictions.
Such a huge leap.
Isn't trying to build a foundational layer for all of future biology a bit delusional? The failure points seem infinite.
The risk is astronomical, and the engineering hurdles from maintaining perfect fluid dynamics across millions of microscopic channels to preventing massive data bottlenecks are immense. But that is the nature of a moonshot. If you aim to just build a new drug, you might succeed, and you help a few thousand people. But if you aim to build the infrastructure of biology, and you succeed, you don't just win a market, you define the next century of science. You create an internet of cells where biological experiments are universally standardized, reproducible, and incredibly fast.
And if they pull off the infrastructure, what is the ultimate output? What does humanity actually get from all these server farms of living cells? The grand prize described in the text is something called the Living Cell Atlas.
We currently have various cell atlases that act like encyclopedias. They list all the types of cells in the body. Here is a liver cell, here is a nerve cell, here are the proteins inside them, but they are static.
Just lists of parts.
Right. The living cell atlas would be a library of cellular destinies.
It maps the trajectories.
It would map the total landscape of how human cells behave across time under any conceivable condition. If you deprive a specific heart cell of oxygen, what exact epigenetic steps does it take over the next 48 hours to survive? And when exactly does it cross the point of no return and die?
Or for cancer.
Right. If you hit a melanoma cell with an immunotherapy drug, what are the 5 different ways it might try to camouflage itself?
And clinically, for the listener, this translates to the absolute end of guesswork in medicine. The authors paint a vision of the future that is just breathtaking. Imagine you get a devastating cancer diagnosis.
Okay.
Today, the doctor looks at statistical averages and says, we are going to start with drug A. It works for 60% of people. We will do a scan in 3 months to see if it's working. You spend 3 months suffering toxic side effects, only to find out you are in the 40% where the tumor grew anyway.
It's agonizing. But under the PreciGenetics model, the trial and error happens outside your body. You get a biopsy. Your actual living cancer cells are loaded into the COMPASS system. The microfluidics divide your cells into 50 different streams, and the machine tests 50 different combinations of drugs on your living tissue simultaneously.
And AI watches how your specific cells react. It doesn't look at a statistical average, it looks at your cellular movie.
The AI monitors the optical signatures and identifies which drug combination successfully kills the bulk of the tumor, while also definitively identifying and neutralizing the 1% of dormant stem cells that would have caused a relapse in 5 years.
That's incredible.
The doctor receives a predictive report, and you are prescribed a targeted therapy that is mathematically proven to work on your specific tumor biology before you ever swallow a single pill.
You avoid months of toxic, useless treatments. But the true paradigm shift, and this blew my mind, is something called adaptive therapy. Because cancer is an evolving system. Treating it shouldn't be a one-time strike.
Adaptive therapy treats cancer the way a grandmaster plays chess. If we connect this to the bigger picture, if you know the rules of the game, if the living cell atlas maps out all the possible evolutionary moves a cancer cell can make, you can anticipate it.
You stay ahead of it.
Exactly. The doctor gives you drug A. The AI predicts that in response to drug A, your cancer will attempt to survive by unpacking a specific genetic pathway.
So before the cancer even finishes unpacking that pathway, the doctor introduces drug B, which specifically targets and destroys cells using that new pathway.
You block the escape route before the cancer even reaches it. You continuously adjust the chemical environment, forcing the tumor down evolutionary dead ends until it is completely trapped and eliminated. It shifts medicine entirely from a reactive, defensive posture into a proactive, predictive engineering discipline.
Think about the history of aviation. Early flight was a terrifying era of trial and error. People strapped themselves into canvas and wood machines, jumped off hills, and crashed constantly because they were guessing at aerodynamics. They were flying blind.
Totally blind.
Today, commercial flight is statistically the safest way to travel. Why? Because we mapped the physics. We built sensors, telemetry, wind tunnels, and computer simulators. Flight became safe because it became perfectly predictable.
Medicine is currently still in the early, dangerous days of aviation. We are flying in a biological fog, guessing at wind currents. The COMPASS platform, the photonics, the AI, they are the radar, the telemetry, and the wind tunnels for the human body.
It's an incredibly hopeful vision. But any time we discuss a technology with this much predictive power, we have to look at the horizon and see the ripple effects. A tool that fundamentally decodes life doesn't just stay in a laboratory, it rewrites the economics and the ethics of human society.
The economic implications discussed in the source are massive. We currently live in a healthcare system driven by scarcity and late-stage intervention. Healthcare is exorbitantly expensive, primarily because we wait until a disease has caused systemic catastrophic damage before we try to fix it.
We wait for the disaster.
We are paying to rebuild the house after the fire has already burned the frame.
And we talked about the billion-dollar drug lottery. Pharmaceutical companies spend billions on drugs that fail 97% of the time, and they have to pass those losses onto the consumer by charging exorbitant prices for the 3% that actually work.
If the infrastructure PreciGenetics is building succeeds, we enter an age of abundance in healthcare. If you can predict drug efficacy in days instead of decades, the cost of research and development collapses.
Yes, sir.
Furthermore, if you can continuously monitor high-risk patients and intercept a disease at the microscopic level, putting out the fire while it's still a single match, the need for massive, expensive, late-stage surgeries and systemic chemotherapy drops precipitously.
You shift the entire global model of healthcare from expensive, desperate emergency response to cheap, continuous maintenance. That sounds like a utopia. But the source document is very measured, and they spend considerable time discussing the ethical shadow of this technology.
Yeah.
Prediction is a deeply complicated double-edged sword.
It is perhaps the most profound moral dilemma of predictive biology.
Exactly.
We have to consider the right to know versus the right not to know.
I thought about this for hours after reading the text. Imagine it's 10 years from now. You go in for a routine physical, they take a small blood sample, run it through the Compass AI, and the doctor says, based on the trajectories of your cellular epigenetics, we predict with 98% accuracy that you will develop a highly aggressive, untreatable neurological decline in exactly 7 years.
It is a staggering psychological burden. Does knowing the information empower you to plan your life and seek experimental treatments, or does it completely destroy the remaining healthy years you have?
Right.
You spend 7 years living in an agonizing countdown. The technology gives us the power to see the future of our biology, but human psychology is not necessarily equipped to handle absolute certainty about our own demise.
And it forces the question, if this data exists, who else gets to look at the telescope?
Yeah.
Because the potential for biological surveillance is terrifying.
The risk of discrimination is profound. If predictive biological trajectories become a standard data point, what happens when health insurance companies gain access to it? They could deny coverage to a perfectly healthy 30-year-old because an AI flagged their cells as being on a 10-year trajectory toward a costly autoimmune disease.
That's dystopian.
What happens when employers require a cellular scan before hiring you for a long-term executive role and subtly pass you over because your biological forecast looks slightly risky?
It creates a new invisible caste system based entirely on the probabilistic math of your cells. The authors are incredibly clear-eyed about this. They point out that the technology itself is morally neutral. It is just a tool to telescope. The telescope isn't good or evil for showing you a meteor heading toward Earth.
But how society chooses to govern the data generated by that tool will determine whether we build an age of abundance or an age of biological dystopia. The text emphasizes that predictive healthcare infrastructure must be treated as a fundamental public good, heavily guarded by privacy laws,
It can't be monopolized.
and not allowed to become a luxury weaponized by corporations or restricted only to the ultra-wealthy seeking radical life extension.
Power must be married to compassion. If you build a machine that reads the language of life, you have an ultimate ethical responsibility to ensure that knowledge is used to reduce human suffering universally, without exception.
It requires a level of societal maturity that we will have to develop in tandem with the technology.
We have covered an immense expanse of territory today. We started by challenging the very nature of disease, redefining cancer not as a static invader, but as a hyper-evolving civil war, adapting within the 40 trillion cells of your body.
We examined the fatal flaw of the snapshot era, the destructive, blinding necessity of killing biology to study it, and how the convergence of label-free photonics and microfluidics offers a way to continuously film the movie of life without touching it.
We looked at the tyranny of averages and how bulk biology hides the deadly minority of dormant cells that cause relapse, proving that true cure requires tracking single-cell trajectories. And we saw how feeding this dynamic time series data into artificial intelligence could create a living cell atlas, predicting disease response before it happens, and replacing trial and error medicine with proactive engineering.
And finally, we explored the incredible audacity of founders like Parmita Mishra, who are risking everything not just to build a product, but to construct the foundational AWS of biology, an infrastructure that will force us to confront profound new economic and ethical realities.
Your body is a living, breathing, microscopic universe. For the entirety of human history, it has spoken a language we couldn't hear, making decisions in a dark room we couldn't illuminate. Now, for the first time, we might actually be building the lens to watch it think. But I want to leave you with one final thought to mull over as you go about your day.
It's the philosophical ultimate endpoint of this journey.
Exactly. For thousands of years, our art, our philosophies, our urgency to love and create and build have all been shaped by the ever-present shadow of unpredictable illness. The suddenness of mortality is woven into what it means to be human. If we reach a point where disease is no longer a terrifying mystery in the dark, or just a trackable, predictable, preventable data point on a screen, how does that change who we are? If the shadow of sudden, unpredictable biological failure is finally lifted, what will humanity choose to build next? Thank you for joining us on this deep dive.